All right, so now we're going to work on our integrating techniques, new ways to find antiderivatives that are going to make our life easier. And the biggest technique of all that you're going to be using most throughout 21B and beyond is called the substitution method. So let me introduce that. Let's consider this integral, the integral of 2x times the quantity x squared plus 5 times dx. And this integral, I really would not, given the choice, I probably wouldn't use the substitution method, but I'm going to show you two ways to do it, one of them using substitution to convince you that it works. I think the easiest way to do this one is to simplify 2x times x squared plus 5 first by simply multiplying, distributing the 2x. You'd get 2x cubed plus 10x. That's easy enough to integrate. We could use our power rule. 2 stays there, that's x to the 4th over 4. 10 stays there, x squared over 2, plus a constant. And of course, I could simplify that to x to the 4th over 2 plus 5x squared plus a constant. Now, let's see how this would look if I was using the substitution method. And so what that involves is making a substitution. You can use any letter you want. The most common one is u. So we're going to let u, this part of the integral, equal x squared plus 5. Okay. Now when we do that, what we want to do when we integrate, right, thinking of this dx, we have two interpretations of that, right? Back when we were talking about area, the dx represented the thickness of a rectangle. In terms of integrating, finding antiderivatives, it tells us what variable we will be integrating with respect to. So if we make the substitution where x squared plus 5 is u, we're committing to changing this entire integral in terms of u's and du's. We need to get a du so we can integrate with respect to u. Well, what is du as well? It's the derivative, right? If I take the derivative of u with respect to x, I would just get 2x. So if I solve it for du by just moving the dx over, I get 2x dx is what du equals. Now notice, x squared plus 5 was my u, and I just happen to have a 2x times a dx left over, which I could replace with du, right? So this part's u. Here we go. I'll just uncover this. This part's u, and the 2x times dx becomes du. And now I can integrate u times du with respect to u would integrate to u squared over 2 plus a constant. And then the idea is, once I found my antiderivative, I can plug my original u back in for u. So that would be x squared plus 5 squared over 2 plus c. Now my claim is that this answer right here, this x squared plus 5 squared over 2 plus c, is the same as this answer. They don't look the same. So what I'm going to do is I'm going to convince you, if I FOIL this out, I get x to the 4th plus 10x squared plus 25 over 2 plus c. And if I split this up, right, one term in the bottom, I can divide it up. I get x to the 4th over 2. This becomes 5x squared plus 25 halves plus c. Now, if you look now and compare these, they do almost look the same, except for this one has an extra 25 halves. And I wanted to show you that because even though they still don't look exactly the same, we can justify these answers as it being exactly the same. Why? When we put c here and we put c here, c represents a constant. We don't necessarily mean that this constant is the same as that constant, right? So the idea is 25 over 2 plus c is a constant. So I could take those two constants and replace those and just call that c, right? I could call this c. So one of the terms we say is the 25 halves can be absorbed into the constant, meaning you could take 25 plus c and just call it c, and then they would have looked exactly the same. So if you get And this is important to know because if you're doing a problem like this, and let's say you simplify and get this answer, and the back of the book did a U substitution and got this answer, you might think you're wrong because you don't see that 25 halves there. And so what you should know then is that if your answer is different from somebody else's by just a constant, then you're okay. That's actually fine. Let's practice some more U substitution. Okay. So how do you know when to use U-substitution? Unlike the previous one where I was able to distribute, that you don't really gain anything. You can't really distribute 3x squared. I guess you can, but you have to put it in as a 9x to the fourth. That doesn't really help you, okay? This is not a polynomial. This is the square root of some stuff. So U-substitution really would be the best technique, okay? Now, what do I let U equal? A good rule is things in parentheses oftentimes would be good choices for you. I could always think of 1 plus x cubed, the square root of that as 1 plus x cubed raised to the 1/2. So that's kind of like parentheses there. What we'll find with antiderivatives, unlike with derivatives, is the rules are not as clear cut. When you take derivatives, the rules are very clear. If you've got a product, you absolutely can use a product rule every single time, and you will get the right answer. With antiderivatives, it's not always so clear. Like, I could tell you that that's why I said usually U equals stuff in parentheses. There are exceptions, okay? These are a little more like puzzles. Now, we'll talk about some other telltale things to look for when, how do you know, that would tell you how you would know you should be using U substitution. Okay, so we're gonna let U equal to 1 plus x cubed. So this now becomes the square root of U. The rest of it, the 3x squared dx, needs to somehow be converted into a du. And it's a perfect match, right? If I take the derivative of 1 plus x cubed, it's really du dx, but we're going to always multiply the dx over to the other side. So du would be 3x squared dx, which is a perfect match with what's left over in the integral. So that part becomes u. Remember, this is multiplication. The order of multiplication doesn't matter. So if I move the 3x squared over here next to the dx just to make it look nicer, that's fine. And that becomes du. This is now u to the 1/2. That's du. Once you convert it to u's and du's, you can use your power rule in this case to find your antiderivative, plus c. After you found your antiderivative, then you replace your u back in, and you get your final answer. Let's look at another one. Integral of tangent cubed times secant cubed. There's no parentheses here. So what's the other thing I should be thinking about with U substitution is, as you've seen, whatever part I let U equal, the rest of the integral somehow has to accommodate my du. So in that sense, the best choice for this problem would be to let U equal tangent of x. Why? Because the derivative of that is secant squared x dx, which is sitting right here. Okay, so if you notice that one part of the integral is the derivative of some other part, then that should tell you, help you figure out what u should be. Also realize I don't need to let u equal tangent cubed. It's enough to just let u be tangent of x, because I can always just think of this as u cubed, and I can integrate that, right? That becomes u to the 4th over 4 plus c, and then substitute back in your u. You've got your answer. Here's another one. Ln of x over x dx can be thought of as ln of x times 1 over x dx. So the thinking here would be, if I let u equal ln of x, du is 1 over x dx, which is another perfect match sitting right there. So this integral can get converted into u times du. antiderivative using the power rule. Remember, that's u to the first. So you would power up, make that u squared over 2 plus c, and then substitute back in to get your final answer in terms of x. Okay. Whoa, let me move this up. So from our previous answers, u sub will work when the derivative of one part shows up somewhere else in the integral, as we've seen. This is like a summary of the last three problems. Right, this was my u, du was sitting right there, 3x squared dx. U is equal to tangent x because du, the derivative of tangent, was sitting right there. U is equal to ln of x, why? Because the derivative of ln of x is 1 over x dx is sitting right there. But what if the derivative of one part isn't exactly the same as du? As long as you take the derivative of your u, as long as it only differs by a constant of what you have left over in your integral, we can work with it. So let me show you how this works. I have x to the fourth times x to the fifth plus 2 raised to the seventh times dx. I'm going to let u equal x to the fifth plus 2. My du, the derivative of that, is 5x to the fourth dx. But notice, if this is u to the seventh, all I have left over is an x to the fourth dx. I don't have that 5, right? I'm missing the 5. Okay, what I did here is I moved the x to the fourth over just to make it really obvious. I'm missing this 5 to make it a perfect match. Now there's several different methods for how to proceed with u substitution when you don't quite have du, when you're off by a constant. It doesn't matter which technique you use. If your professor uses something different than what I'm going to show you, and it works for you, that's fine. What I usually ask students is, who would want to see what I think is the fastest and most efficient way to run u substitution? Most students agree that's the method they want to learn. So that's the one I'm going to present. But again, you can, if you learn it a different way, it's totally fine as long as it works. So I call this the Whishing Technique. If you've had me for 21A, you may recognize that. We use that term for another, for doing a limit problem involving sine x over x. It's a similar idea. Okay, so the idea is I'm missing a 5 here. I wish I had a 5 there. That's what I'm wishing for. So let's put one there, okay? Now, if I put a 5 there, to get this part to match up with my du, that's changing the problem unless I compensate by multiplying by 1/5 somewhere, because 5 times 1/5 is just 1. Now the best place to put that compensating 1/5 is outside the integral. Remember, constant multiples can be pulled out of your integral. So I'm going to leave the compensating there. Notice 5 times 1/5 is just 1, so I'm not changing the problem. But in doing so, what I now have is this 5x to the fourth dx is now can be replaced with du. They're equal to each other. The 1/5 will stay there. And now I have my integral in terms of u's and du's, and everything else is the same. To integrate this, the 1/5 stays there. Antiderivative is u to the 8th over 8 plus c. And then you could replace your u back. I combine this to make it 1/40th, x to the 5th plus 2 to the 8th plus c. One drawback with my method is it can be confusing where you're working a problem and you go back and you look at it and you say, well, where did that 5 come from, right? It wasn't in the original problem. So what I recommend, here I'm using a different color. That's, if you have 2 different colors of pen, that would be great. But at the very least, what I like to do is circle it. I circle it, and that's my cue. When I go back and study this problem and try to retrace how I got this answer, when I see something circled, that means I put that there. I wished for that 5, and then I compensated with that 1/5. Okay, so I try to circle anything extra that I add. Let's see it again. want to integrate x over 3x squared plus 4. I see that if I let u equal the whole denominator, the derivative of that is 6x dx. And I have an x dx here, but I'm missing the 6, right? That's not showing up there. So I would use my wishing technique. I'm going to wish for the 6 right there next to the x to match up with my du. Compensate with a 1/6 outside. The 6x dx right here, okay, I often compare this to, because some people get confused on this step, it's like exchanging 4 quarters for $1. 4 quarters don't look the same as $1, but they're the same, right? They're equal to each other. In the same way that $1 equals 4 quarters, 6x dx equals du. So I'm going to exchange that. The 6x dx, I'm exchanging it in for a du, exchanging 4 quarters in for $1. The bottom was u, the 1/6 stays out there. Recall that the antiderivative of du over u, or 1 over u du, is ln of the absolute value of u plus c. It just so happens that 3x squared plus 4 is never going to be negative, right? If you square something, times it by 3 and add 4. So you really don't need the absolute value here. Certainly if you put it, it's not going to hurt. All right, lots of practice on this. Next one, I want to integrate secant squared root x over root x dx. This time I'm going to let u equal just the root x. And my reasoning here is I can integrate secant squared of u. I know that's tangent's derivative, so I just want this to be my u. The derivative of u is 1/2 x to the negative 1/2 dx. And if I rearrange this problem, if I take this other root x and bring it up as x to the negative 1/2, bring that up here, the only thing I'm missing now is this 1/2, right? To make this a perfect match for du, I'm missing the 1/2. So I'm going to wish for the 1/2 and then compensate with a 2 outside this time. The 2 stays there. The 1/2 x to the negative 1/2 dx gets exchanged for a du. And my antiderivative of 2 secant squared u du is 2 tangent of u plus c. Plug in my u. Another one. E to the 1 over x squared over x cubed. I'm going to let u equal 1 over x squared, otherwise known as x to the negative 2. My derivative is negative 2x to the negative 3 dx. And I can see I can make this an x to the negative 3 if I bring it up. So I brought up the x to the negative 3 there, but I was missing the negative 2, so I put one there, compensated with a negative 1/2 outside the integral. And my integral now becomes negative 1/2 times the integral of e to the u du. Remember, the antiderivative of e to the u is your favorite integral. It's just e to the u. So negative 1/2 e to the u plus c. Put your u back in and you're done. Oh yeah. I mentioned that the rules are not as clear-cut. Oftentimes, when you have a fraction, I did one earlier, your u would be the denominator, the one I did a couple of problems ago. But that doesn't always work. If I let u equal 1 plus x to the 4th, which is a good thing to start with, my du would equal 4x cubed dx. And all I have left over in the numerator would be x times dx. Now, I want to be clear about this. You might think, hey, I could get 4x cubed dx if I wish for a 4x squared and compensate with a 1 over 4x squared. That is not allowed. Okay. While in life you can wish for anything, when you're doing the wishing technique with U-substitution, you're only allowed to wish for constants, okay? So you can't wish for variables or functions. So that's not going to work. So we have to think a little bit outside of the box. If you think of the x to the fourth as x squared squared, then I could let u equal just this x squared, and my du would be 2x dx, and I have an x dx there. So all I have to do is wish for a 2, compensate with a 1/2. 1/2 stays there, exchange the 2x dx for a du, and hopefully you recognize 1/1 plus u squared is the derivative of inverse tan of u. So the antiderivative is 1/2 inverse tan of u plus c. And then you replace your u back. Now, what if you have leftover x terms? So for example, I want to integrate x times x minus 3 to the 5th. Seems like a logical choice for you would be the parentheses, just x minus 3. du for x minus 3, the derivative of x is just 1, so du is equal to dx. So as an intermediate step, this is now u to the 5th, dx gets replaced with du, but I have a leftover x that's unaccounted for. When that happens, sometimes, hopefully, not all the time, if you have a leftover x, if you go back to your original choice for u, and you solve this for x in terms of u, x would be u plus 3. If you can replace this x in terms of u, then that would be fine. So we're going to replace that x with u plus 3. Now I can distribute my u to the 5th to get u to the 6th plus 3u to the 5th. Integrate, and once you find your antiderivative, plug back in to get a final answer in terms of x. All right, one last thing here on U-substitution. When you're doing U-substitution with a definite integral, we haven't done any definite integrals yet, we've done indefinite integrals. You have to be careful with the limits of integration. So let's look at this integral, 3x squared over 1 plus x cubed all raised to the 4th dx. I want to integrate that from, remember these are x limits, x equals 0 to x equals 2. We don't usually write the x equals there, but those are x limits. Okay, it's a fairly easy u substitution. If I let u equal 1 plus x cubed, du is equal to 3x squared dx, which is a perfect match in your numerator. You don't have to wish for anything. Now you have a couple of options. If you choose not to change the limits of integration, then, let me do this. Let me walk through one of them this way. Here's what you want to do. The integral has the form of u to the 4th on the bottom. It's du over u to the 4th. Do not put the 0 and the 2. And the reason why are those are x limits. But right now we're in the language of u, right? We're in terms of u. So you would not be correct to put 0 and 2 there. Instead, you can just do it how we've been doing. Find your antiderivative, which is if you bring that up, u to the negative 4, antiderivative of that, if you raise 1, u to the negative 3 over negative 3. Then what have we been doing? We've been putting it back in terms of x. Now that you're back in terms of x, then yeah, you would evaluate this from x equals 0 to x equals 2 and get your final answer, 9 to the negative 3 over negative 3 minus 1 to the negative 3 over negative 3. I know that can be simplified, but that's not important at this point. Now the other option is to convert your limits in terms of u. And how you do that, okay, if we convert these limits in terms of u, then that's fine. So what you do is you take your limits. So when x equals 2, if this is your u substitution, if u equals 1 plus x cubed, if you plug in 2 there, 1 plus 2 cubed gives you u equals 9. When x is 0, 1 plus 0 cubed gives you u equals 1. So you can put 1 to 9 there for u. There is one slight advantage to that, is when you find your antiderivative, which we already did, you don't need to convert back to x, because you could just evaluate this from u equals 9 to u equals 1. And notice we get the same answer, right? So by converting the limits, you save this step of changing it back to x and then plugging in. You save one step. My experience, though, is it's not worth the confusion. If it hasn't happened yet, I guarantee it will in lecture. What'll happen is this integral will start, because remember, I put x equals 0 and x equals 2, and I emphasized u equals 1 and u equals 9. What will happen in lecture, 99 times out of 100, the professor will write the integral from 0 to 2, they'll do a u-substitution, and they won't even write, and all of a sudden the limits become 1 and 9, and they won't show this. So, and everybody gets confused. They're looking at each other like, wait, how did the 0 and 2 change to a 1 and a 9? I've seen that time and time and time again. So my personal preference is it's not worth the confusion that results by changing the limits. However, if you get good at it, you can save a step. That might be a time saver. And I think you at least need to be aware of it, because your professors will almost always, when they do a u-substitution, convert the limits in terms of u. That way you'll know when you see different numbers show up on your integral, you'll know what they did to get those numbers. All right, that's a good for now.